Okay, so in this video we'll be doing the Themra 1.2 for the stochastic processes, and the topic is Poisson processes. Okay, so Themra 1.2 states that let n, capital N, be a Poisson random variable RV, okay, with parameter of mu, okay, and conditional on n, this random variable, there is another random variable, okay, there is m, which has a binomial distribution, which follows binomial distribution with parameter capital N and P. Okay, this is the number of trials, capital N, and P is the probability of success. Okay, because in binomial distribution we have two things: number of trials, capital N, and P, which is the probability of success. Okay, then the unconditional distribution of m, the second random variable m, okay, is also Poisson distribution with parameter mu and p. Okay, we have two random variables. Okay, the first one is capital N, which follows a Poisson distribution with parameter of mu, but we have another m, which have a binomial distribution with parameter capital N, which is the number of trial, and P, which is the probability of success. Okay, and it is conditional on n. Okay, so then the unconditional distribution for m is also Poisson, but here for n we have the parameter of mu, but for m the parameter will be mu and p. It means that probability of m is equal to e raised to the power minus mu p multiplied by mu p raised to the power k divided by k factorial. Okay, same like an ordinary Poisson random variable. For example, probability of n is equal to n, small n, or k is equal to e raised to the power minus mu dot mu raised to the power k divided by k factorial. N is equal to k. Okay, the parameter will change from mu to mu p. Okay, so this is the whole kind of situation in the theorem 1.2. It relates the two random variables, which has one random variable first is following a Poisson distribution with parameter mu, and the second is conditional on m but n, but it is following a binomial distribution with parameter m, n, and p, where n is the number of trials and p is the number of successes per trial, okay, or the probability of success. Okay, Now I will explain it in some layman term so that you understand it, and I will also try to prove this thing from this. Okay, so let's prove it. Okay, proof of it. Okay, so we know that probability of n is equal to n, small n, it is equal to e raised to the power minus mu dot mu raised to the power n divided by n factorial. Okay, this is something that we know from the Poisson distribution. Okay, this is exactly the Poisson distribution where n is equal to 0, 1, 2, 3 and so on. Okay, now given that n is equal to n, this is already given that it is n is equal to n, then the probability that capital M is equal to M such that n is equal to n, this is equal to we know that this M follows a binomial distribution, so it will be equal to n combination of M probability raised to power m into 1 minus probability raised to power n minus m. Okay, while the small m, it has a value between 0 and n. Okay, this is the binomial distribution, this is the Poisson distribution. Okay, there is nothing there's nothing added in it. This is purely Poisson distribution from by definition, and this is the binomial distribution. Okay, now we will use both these distributions to prove that probability that m is equal to small m or k, it will be equal to e raised to power minus mu p into mu p raised to power k divided by k factorial. Okay, so probability that m is equal to m such that n is equal to small n. Okay, this is equal to this very thing. Okay, binomial distribution, but probability of m is equal to m, the unconditional one, this is the conditional. Okay, so the unconditional one, it will be equal to summation of n is equal to m up to infinity probability of m is equal to m such that capital N is equal to small n multiplied by probability of capital N is equal to n. Okay, now we know that this is equal to this thing and this is equal to this thing, so putting both the values over here, so probability of capital M is equal to small m, it will be equal to summation of n is equal to m up to infinity n combination of m. Okay, writing the binomial function over here into 1 minus p raised to power n minus m multiplied by e raised to power minus mu raised to power n divided by n factorial. Okay, and we know that n m is equal to n combination of m, and it is equal to n factorial divided by m factorial into n minus m whole factorial. Okay, so substituting this into this thing, writing this instead of n combination of m. Okay, so what we get when we substitute we get that the probability of m is equal to small m, it is equal to p raised to power m into 1 divided by m factorial. Okay, summation of n is equal to m up to infinity n factorial divided by n minus m whole factorial. Okay, into 1 minus probability raised to power n minus m dot mu raised to power n dot e raised to power minus mu divided by n factorial. Okay, we can also simplify it before writing into this form. Okay, what I did was I actually this 1 over m factorial was over here. Okay, so I took it outside. Okay, just I made the small fragments of it. Okay, so don't be confused with it. Let me write it into the previous form and then I will. Okay, writing it into the previous form actually. So what is the previous form? The previous form is probability of m is equal to small m, it will be equal to summation of n is equal to m to infinity. Okay, and then we will have n factorial divided by m factorial into n minus m whole factorial. Okay, we wrote this thing instead of n this thing. Okay, just replace it with this and I will write now this thing as it is. Okay, pm into 1 minus p raised to power n minus m multiplied by the mu raised to power n e raised to power minus mu divided by n factorial. Okay, so now we can transform this thing. This will go outside. Okay, that m factorial will also come outside. Okay, and then we write all the other things into inside this thing. Okay, that is what I meant. Okay, I will continue that in the next video. Okay, so this n factorial, it will be cancelled with this one. Okay, so n factorial will cancel the n factorial. Now we can write it as the probability of capital M is equal to small m, it will be equal to probability raised to power m multiplied by 1 over m factorial. Okay, summation of n is equal to m to infinity. Okay, 1 divided by n minus m whole factorial into 1 minus p raised to power n minus m mu raised to power n dot e raised to power minus mu divided by, sorry, n factorial is already cancelled, so we don't need to write it. Okay, now taking n minus m is equal to k. Okay, it means that m is equal to k minus n. Okay, also n is equal to m plus k or k plus m. Okay, so we will use all these terms interchangeably. Okay, now replacing n minus m with the k, so what we get is, we get probability of m is equal to m is equal to probability of m is power m dot 1 over m factorial. Okay, summation of, this is n is equal to m. Okay, so we know that n minus m is equal to k. Okay, so we will take this m into this side, so it will become n minus m is equal to, and it will become equal to k, so it will be k up to infinity, or k is equal to 0 up to infinity. Okay, mu raised to the power k plus m, okay, multiplied by e raised to power minus mu divided by k factorial. The n minus n factorial will become k factorial. Okay, multiplied by 1 minus p raised to the power, this is n minus m. Okay, so n minus m will become k. Okay, so okay, you must be wondering like how I get k plus m. Okay, so n, this is mu raised to the power n. Okay, so n is equal to m plus k, so I write m plus k are k plus m, which are both okay. Okay, so now what we do is we can write mu raised to power k plus m or m plus k as mu raised to power k multiplied by mu raised to power m, because it is the law of multiplication. Okay, when the bases are same, the powers are added. Okay, for example, 2 raised to power m multiplied by 2 raised to power n, when the both are multiplied you will get 2 raised to power m plus n. Okay, so using this law we can write this k plus m as mu raised to power k dot mu raised to power m. Okay, I will continue this into the next video. Okay, this video is becoming long. Okay, so using this law what we do is we rewrite it. Okay, okay, this is 1 over m factorial summation of k is equal to 0 up to infinity mu raised to power k dot mu raised to power m dot e raised to power minus mu divided by k factorial into 1 minus p raised to power k. Okay, now this mu raised to power m, it will come to this side, so it will become p raised to power m dot mu raised to power m divided by m factorial, okay, e raised to power minus mu summation of k is equal to 0 up to infinity e raised to power minus mu into, sorry, this is not mu raised to power k, mu raised to power k into 1 minus p raised to power k. Let me rewrite it. Mu raised to power k into 1 minus p raised to power k divided by k factorial. Okay, so p raised to power m dot mu raised to power m divided by m factorial into e raised to power minus mu summation of k is equal to 0 up to infinity mu raised to power k into 1 minus p raised to power k divided by k factorial. Okay, this is also k and this is also k. Okay, so we can write this term as mu into 1 minus p raised to power k. Okay, because mu have also the power of k and 1 minus p has also the power of k. Okay, divided by k factorial. So rewriting this in this form, what we get is probability of capital M is equal to small m is equal to probability raised to power m mu raised to power m divided by m factorial and this is summation of k is equal to 0 up to infinity mu into 1 minus p raised to the power k divided by k factorial. Okay, this term, the second one term, this is the Taylor expansion. Okay, and this can be reduced to the form of this is equal to e raised to the power mu into 1 minus p. Okay, this is equal to this thing. Okay, so now writing it in that form we get p raised to power m mu raised to power m divided by m factorial e raised to power minus mu e raised to power mu into 1 minus p. Okay, so now probability of capital M is equal to m is equal to probability raised to power m mu raised to power m divided by m factorial into e raised to power minus mu dot e raised to power mu and e raised to power minus mu rho. Okay, this mu will be multiplied by 1 minus p, so it will become e raised to power mu minus e raised to power minus mu p. Okay, so now this is minus mu and this is plus mu, so as the bases are same, so it will be added, so minus mu plus mu, it will become 0, so e raised to power is equal to 1. Okay, so probability of capital M is equal to probability raised to power m mu raised to power m divided by m factorial into e raised to the power 0 dot e raised to power minus mu p. Okay, now I write it as the probability of capital M is equal to small m is equal to p raised to power m mu raised to the power m divided by m factorial multiplied by 1, as e raised to power 0 is equal to 1. Okay, multiplied by e raised to power minus mu p. Okay, now this and this power are same. Okay, so we can write it as probability of m is equal to mu p raised to power m, because powers are same. Okay, multiply by e raised to power minus mu p divided by m factorial. Okay, so we see that, and also using the Poisson distribution. Okay, Poisson distribution, which states that the probability of n is equal to k. Okay, it is equal to mu raised to the power k dot e raised to the power mu divided by k factorial. Okay, so here the what we say, the parameter is mu p, here the parameter is mu, here the power is mu p, here the power is only mu, and we have k factorial and we have m factorial over here. So it means that it also follows the Poisson distribution. And with the parameter of mu p. Okay, which is proved over here. Okay, so whenever we have like two random variables n and m, okay, while n follows the Poisson distribution and m follows the binomial distribution, okay, then the unconditional distribution of m, okay, while m is conditional on n, then the unconditional probability of m will be also Poisson distribution, but only the parameter will be changed. The parameter will become mu p. Instead of mu, it will also include the probability p. Okay, so that is the whole definition of this theorem. Now I must kind of conclude it in the layman terms. Okay, in layman terms, we can say that, like, imagine like you have a factory, okay? You have a factory where defects occur randomly at 10 defects per day, okay? This is the lambda, okay, the rate of this action. Okay, I was explaining that we have a factory and there are defects occurring randomly at 10 defects per day, okay? Now this is the Poisson distribution because we have a rate of an action, okay? 10 defects per day, it means that it is a Poisson distribution function, okay, with the mean rate mu is equal to 10 per day, okay, 10 defects per day. The parameter mu is equal to 10 per day, okay? Now we have another variable, okay, random variable. It is the random variable, that random variable is that we have 30% chances that the defects are major ones, okay? So it means that whenever this random defect occur, there is 10% chance that there is 30% chance that the defect is major, and 70% of the time it is a minor defect, okay? So now taking this example in terms of this theorem 1.2, okay, this is the first random variable which is following a Poisson distribution. This is the second random variable which is following a binomial distribution, okay? N is the number of trials, so each trials, okay, there is 30% chances, okay, and P is the probability which is 30% or 0.3, okay, and N is the number of trials. So whenever we make the quality control, now I hope you have understood that this is the first variable and this is the second random variable, okay? First one is the first one is, I will say, RV1, okay? This is the Poisson distribution with a rate of 10 defects, while the RV2, okay, it is following N and 0.3, okay? For each trial there is 30% chance that the defect is major, okay? So what happens to the distribution, the second one, unconditional, okay? So this second one will follow the distribution with a parameter of mu and p. Now mu is 10, okay, so I will write 10 multiply by probability is 0.3, okay, so this is 3. So the major defects, okay, which is the second variable, okay, it will follow the Poisson distribution of 3 per day, 3 at the rate of 3 per day. So unconditionally this major defects will follow the Poisson distribution with the rate of 3 per day, okay, while the defects are 10 per day, and there is 30% chances that each trial, and among these defects there is 30% chance that the defect is major, okay? So the unconditional major defects will follow the 3 per day Poisson distribution, okay? We can write it as, this is the same thing as we discussed over here. I hope you have understood. Thank you. Okay, so the what happens in actually this whole scenario is that we take a Poisson distributed random variable, which is the total defects that is happening, okay, with a rate of 10 defects per day, okay, and then apply a binomial filter to it, which is actually differentiating between a major and minor defects, okay, at the rate of actually 30% chances in each trial that is happening over the day. For example, a trial can happen like only once a day, twice a day, thrice a day, or maybe 5 times a day, okay, but in each trial, okay, we have 30% chances that it is a major defect, okay. So then here comes the play for the Poisson distribution that is unconditional. Now we see that the second random variable is conditional on the first one, okay, because whenever there is a defect happening, then we have a chance of major and minor, okay. So that is why when we take the second random variable is unconditional, okay, independent of the first random variable, okay. So what will it will do, it will also follow the Poisson distribution, okay, but the rate will be reduced. The rate will be reduced to mu and p, okay. The first one is has a rate of only mu. The second one, random variable, will independently will have a rate of mu and p together, where p is the probability that we already defined, which is 30%. So multiplying mu with p, it will define the rate for the unconditional second random variable and will also follow the Poisson distribution. That is all about the second random variable unconditional Poisson distribution. Okay, theorem 1.2 explains the very thing that I explained in the layman terms. Okay, but that is mathematically, and here I just concluded it in an example form. Okay, so in this video we will be doing the Poisson process. Okay, so Poisson process by definition actually entails two properties. Okay, the first property, two main properties. Okay, the first one is independence, and the second one property is that it follows the Poisson distribution. Okay, that these two are the main notions that it entails or it consists of. Okay, so let us define the Poisson process. So by definition, a Poisson process is the representation of a stochastic process. Okay, it is a representation of a stochastic process. It means that probability is involved here. We don't know 100% result of an event. Okay, it is the representation of stochastic process that models the occurrence of random events over time. Okay, so what is a Poisson process? A Poisson process is the is a stochastic process that models the occurrence of random events over a time period. Okay, it has three main properties. Okay, the first property, as we discussed, is independence. Okay, independence. It means that over a certain time of period, actually, there may be a number of events occurring. So each event, okay, each event occurring is independent of the previously occurred event. It means that any forthcoming event that is to be happened actually does not rely on the previous event. Okay, so this is the independence property of the Poisson process. Okay, we can write it as the number of events occurring in disjoint time intervals is independent. For example, we have three events occurring. Okay, event A, then event B, and then event C. Okay, so this event B, this does not depend on event A. It does not depend on the results achieved from event A. Okay, this event is independent, this is independent, and event C is independent. Okay, so this is one of the property of the Poisson process. Okay, the second property is stationary. Stationary property of the Poisson process, and this property states that the probability of an event occurring in an interval depends only on length of interval and not on location. It means that it does not depend if the event is occurring preceding to some events or after some events. Okay, it will only depend on the interval, the length of the interval. Okay, the probability will only depend on the length of the interval and not on the location. Okay, and event may be occurring on the in a sequence. Okay, event 1, 2, 3, 4, and so on. Okay, so the position does not is not a concern, only the length of interval is a concern. For example, a customer okay, for example, we have a store. Okay, and there are customers coming. Okay, so the customers are arriving at the rate of 15 customers per hour. Okay, so in this if we have to pinpoint the stationariness of the events actually, so we can say that the event that is occurring actually, which is the number of customers coming into the store, actually it does not depend on the location. It will not depend on whether it is in the morning or in the evening or in the afternoon or anything like that. Okay, but it will depend, like if I say I have to model like 4 hours, okay, so it means that on average there are 60 customers that are coming into the store, okay. So the length of the interval, that is of concern. The location of interval is not of a concern. I hope you have understood the stationary. And the third one is no simultaneous events. So as the name suggests, it means that the events occur one by one or one at a time. Okay, so these three are the properties of the Python process. So in Python process, actually, n of 0 is equal to 0. Okay, these are the properties. It means that initially no event has occurred. Or at time 0, the number of occurrences of that event is 0. Okay. The second one is that n of t, at time t, the number of occurrences is, it follows the Poisson distribution, okay, with a parameter lambda t. Okay, so this is the second, where t is greater than 0. Okay, for t is equal to 0, there is 0 occurrences, okay, which is the first one. Okay, for t greater than 0, the number of occurrences at time t is following the Poisson distribution with the parameter lambda t. Okay, and the increments are independent, okay, which means that n of t plus s, where s is the increment actually, okay, these are independent. Okay, nt is the initial one and n of t plus s is the succession with the increment of s. It means that if we say that like a customer arriving at store is per hour is 15, okay, so for 1.5 hour it should be 1.5 into 15, okay. So these events are independent and follows the Poisson distribution, okay, Poisson distributed with mean of lambda s, okay, where s is increment and lambda is the actual rate, okay. So these three are the properties mathematically. I will also give an example of it so that you understand it, okay, through example, and then I will solve the two examples that are done by the professor. Okay, so now I will give you an example, like the example is customers arriving in a store, okay. So suppose that in a store the customers arrive at a rate of like lambda is equal to 2 per minute, okay. Every minute there are 2 customers arriving, so lambda is equal to 2, okay. So the number of customers arriving in 5 minutes period will be, okay, what we will use is, we will use this n of t, okay. So here t is equal to 5, okay, and lambda, which we already know, is 2 per minute, okay. So n of 5, it will be equal to Poisson lambda 5, and we know that lambda is equal to 2. So putting the value over here, we get n of 5. It means the number of events occurring in 5 minutes, okay. It will be equal to lambda into 5, which is equal to 2 into 5, which is equal to 10. So 10 customers will arrive in a period of 5 minutes, okay. Now extending it, okay, now we want to find the probability that exactly 8 customers arrive in 5 minutes, okay. So for that, we will be using the Poisson distribution, okay. Recall that the probability of n is equal to k, it was equal to mu raised to the power k e raised to the power minus mu divided by k factorial, okay. Or we can also say that in lambda form, okay. In lambda form, we can say that lambda raised to the power k e raised to the power minus lambda divided by k factorial, okay. Both are same, okay. Now here lambda is equal to 2, okay, which is the initial per minute. But we want to find after 5 minutes, okay. So we want to find the probability that n of 5 is equal to 8, okay. So 8 is equal to k over here, and n is equal to n of 5, which is equal to 10, okay, because previously we found it by lambda t, which is equal to 2 into 5 is equal to 10, okay. So n of 5 is equal to 10, that we already found, okay. So here lambda will be equal to 10, k over here is equal to 8, e raised to power minus 10 divided by 8 factorial, because k factorial k is equal to 8, okay. So calculating it, we get, so 10 raised to power 8 will give us about okay, multiply by 2.78, which is the value of e raised to power minus 10, divided by 8 into 7 into 6 into 5 into 4 into 3 into 2 into 1, okay, which is the value of 8 factorial, okay. So solving this, we get about 0.1126, okay. This is the probability that exactly 8 customers are arriving after 8 minutes, okay, after 5 minutes, sorry. So it will become 11.26%. So there are 11.26% chances that after 5 minutes exactly 8 customers are arriving. Okay, so in this video we will solve the first example. Okay, it says that the defects occur along an undersea cable according to Poisson process of rate lambda is equal to 0.1 per mile. Okay, so lambda, which is the rate of the process occurring or event occurring, is 0.1 per mile. Okay, it says that what is the probability that no defects appear in the first 2 miles? Probability that no defects occurs in first 2 miles implies that t is equal to 2 because we have the interval given as 2 miles. Okay, so t is equal to 2 and lambda is equal to 0.1. So when we have such case, when interval is given, we know that n of t is equal to lambda t. Okay, so lambda is equal to 0.1, t is equal to 2, so it is equal to 0.2. Okay, so n of t is now found. Okay, so now it says that what is the probability that no defects occurs in the first 2 miles? Applies that you need to find the probability that n of t is equal to 0. Okay, where t is equal to 2 miles. Okay, in other words, the probability that n of 2 is equal to 0. Okay, so using the probability formula from the Poisson distribution. Okay, so we know that the probability that n of t is equal to k, it is equal to e raised to the power minus lambda t dot lambda t raised to the power k divided by k factorial. Okay, k over here is equal to 0 because we want to find whether the probability that n2 is equal to 0. Okay, so k is equal to 0. So when we put the values, we find that e raised to the power minus lambda t, which is equal to minus 0.2. Okay, and 0.2 raised to the power 0 divided by 0 factorial, so it becomes 0 e raised to the power minus 0.2. Okay, and it gives us 0.8187, or there are 81.87% of chances, okay, that there are no defects in the first 2 miles. Okay, so part 1 is solved. Part B says that if are given that there are no defects in first 2 miles, it means that n of 2 is equal to 0. If n of 2 is equal to 0, then what is the conditional probability that that no defect occurs between mile 2 and 3? It means that we have to find the probability that no defect occurs in the mile between 2 miles and 3 miles. So between 2 and 3 miles there is no defect occurring, while we know that in the first 2 miles we don't have any defect, that is n of 2 is equal to 0. Okay, so for this we know that the Poisson distribution, the Poisson processes actually, they are independent. They do not depend on the previous occurring events. Okay, so simple is that it does not depend on whether in first 2 miles we are getting a defect or not. We just have to need to find out probability of x3 minus x2, which is equal to probability of x1 is equal to 0. Okay, so the probability of x3 minus x2 is equal to 0, this is to be found. Okay, so this is ultimately equal to probability that x1 is equal to 0. Okay, or probability that n of 1 is equal to 0. This x variable that can also be taken as n. Okay, just like we did it as above. Okay, so this x can be replaced by n. That is not a a problem. You can write any of it, either x or n. Okay, so we need to define whether in that 1 mile there is no defect. So we just need to find probability of n1 is equal to 0. So here k is also equal to 0. Okay, so writing it like the first one, e raised to power minus lambda t dot lambda t raised to the power k divided by k factorial. Okay, so lambda over here is same, which is 0.1. Okay, and t here is 1, so we get e raised to power minus 0.1 into 1 dot 0.1 raised to power 0 divided by 0 factorial. Okay, so probability of n1 is equal to 0, it is equal to e raised to power minus 0.1 multiplied by 1 divided by 1. So a is equal to e raised to power minus 0.1, and it gives us a value of 0.9048 or 90.48%. So there are 90.48% chances that there is no defect in the third mile. I hope you have understood this problem. Sorry for my voice. Actually, I had some problem again. Okay, this is the example 2. In this video, we will do the example 2 on page number 271. Okay, it says that customer arrive in certain store according to Poisson process of rate lambda is equal to 4 per hour. Okay, so this is the rate of arrival lambda, which is 4 customers per hour. Okay, next it says that given that the store opens at 9 a.m. Okay, so the opening, this is very important. Okay, opening is 9 a.m. Okay, it says that what is the probability that exactly one customer arrive by 9:30 in half hour, okay? 1 over 2. Because 9 to 9:30 is 1 over 2 hour, okay? And we do it in hours because the rate of arrival is per hour. So 9 to 9:30 becomes 1 over 2 hour, okay? And a total of 5 arrived by Alhamdulillah by 11:30 am. So we need to find the probability, okay? Okay, so what we need to find is we need to find out the probability that n of 1 over 2 is 1. It means that in the first half hour, 1 over 2 hour, we are getting exactly one customer, okay? And n of 9 to 11:30 becomes 2.5 hours, okay? So n of 2.5 is equal to 5. Total of 5. Okay, so now it can be converted into this form. Okay, for the first half hour we are going to exactly 1. This is constant, okay? N of 1 over 2 is equal to 1, okay? But in the next we are getting n of 5 by 2 minus n of 1 over 2 is equal to 4. This is something that we need to find. In the first half hour, we are getting the probability of exactly one customer, and in the next 2 hours, okay, 2.5 hours minus half hour, we are getting exactly 4 customers. So a total of 5 customers, okay, as in the statement. This is need to be found, okay? So how we can find it? We can find it with the same formula that we used in the theorem 1.2 and 1.1, okay? So probability of this is equal to e raised to the power minus lambda t dot lambda t raised to the power k divided by k factorial multiplied by e raised to the power minus lambda t dot lambda t raised to the power k divided by k factorial using the multiplication formula. Okay, so here in the first one, lambda is equal to 4, okay, and t is equal to 1 over 2 r. But here lambda is equal to 4, but t is equal to 2 hours, okay. And k in the first one is equal to 1, and in the second one k is equal to 4. So putting the formulas, e raised to the power minus lambda, so minus 4, t here is 1 over 2 dot 4 into 1 over 2 raised to the power k. K over here is 1 divided by 1 factorial multiplied by e raised to the power minus 4 into 2, because here t is equal to 2 hours, okay, dot 4 into 2 raised to the power k. K over here is 4 divided by 4 factorial. So when we actually simplify it, we get e raised to the power minus 2, okay, and 2 raised to the power 1 divided by 1 factorial is equal to 1, okay. And in the second one, we get e raised to the power minus 8 dot 8 raised to the power 4 divided by 4 factorial, which is equal to 4 into 3 into 2 into 1, okay. So more simplifying it, we get 2 e raised to the power minus 2 multiplied by e raised to the power minus 8 into 512 divided by 3, okay. So it will become this e and this e bases are same, so we get e raised to the power minus 10. So 2 e raised to the power minus 10 dot 512 divided by 3. So 2 into 512 is 1024. So 1024 e raised to the power minus 10 divided by 3. So we get 0.0155 or 1.55% chances that we have one customer exactly in the first half hour and 4 customers exactly in the next 2 hours, okay. So that is how you find it. Thank you.